Thanks. So I'm Josef Richmond. I'm a third year PhD student from the Australian National University, the Space, Plasma, Power and Propulsion Lab. So earlier this year, I visited my co-authors here, Jose Pagan, Shu Wang, Mi Hairani in CU Boulder's Impact Lab to do an experiment on dust charging under UV and plasma. So continuing the same dust charging theme. We've all seen this plot probably a couple times, but the moon is exposed to the solar wind plasma. It's exposed to UV, gamma rays, X-rays, etc. So when you take this environment, get some dust, replicate this in the lab, what will tend to happen is the dust will charge up and it will loft. So when I say loft, I mean it will jump off the surface. So we know you can do this by shining UV. We know you can do this by an electron beam, and it doesn't seem to work when you just use a plasma. The key thing is that you're generating secondaries at that dusty surface, whether they're photoelectrons or secondary electrons. Yeah, so as it turns out, charging a regolith surface is a little bit different than charging a solid surface in the sense that the surface structure and the subsurface structure becomes quite important. And that's all summarized very nicely in that patch charge model. Some of the authors are actually in this room. So what we wanted to do, we wanted to see what happens with dust under both UV and plasma at the same time, kind of like a simulation of the lunar day side. So to that end, we used a xenon excimer lamp, 172 nanometer central wavelength. We generated a plasma in argon gas with just a hot DC filament, so a low density DC plasma. And then basically what we did is we exposed our dust to the plasma, exposed it to the UV, and then exposed it to both the UV and the plasma at the same time, and watched what happened with just your standard video camera. So I've got some videos of that I'm going to show you. I'm not going to show you what happens with just the plasma. Nothing happens. It's a video of dust not moving. We don't need to see that. But here is the UV only. You can kind of see it. There's some lofting. Those particles are jumping. This isn't new. This has been shown before. The interesting thing is what happens when you add the plasma. So something happens, a lot more jumping, right? This is the same plasma that caused no movement by itself. So what we did is we count the number of particles that are lofted. As you can see with the plasma, nothing happening. But for some reason, when we add that plasma to the UV, we get about a 3 times increase in mobility. Like I was saying before, we think the mobility is related to the generation of secondaries. That plasma, the electrons in there will generally not have enough energy to produce secondaries, so something else is going on. To understand that, we look at the simplest case sort of forces on our dust particles, and we think about what might have changed. We probably haven't changed gravity. We haven't changed the cohesion. So we look at the lofting forces. So the first one is the sheath force. That's just the force of the plasma sheath or the photoelectron sheath acting on our charged dust particles. The second one is just the repulsive force between like charged dust particles. The first thing we checked is the sheath there. So we just use an emissive probe and basically get the potential as a function of height above that dusty surface, which is what you're seeing on the left-hand side. And from that, we can back out the electric field. Now, when we go from the plasma to the UV plus plasma, there is some difference. It's about 300 volts per meter. And I should also mention that with the photoelectron sheath, it's going to have an opposite orientation. So it's actually going to tend to oppose lofting if you have negatively charged dust particles. So we're cheating a little bit. We actually have an idea of what the charge on the dust under this same UV lamp should be from previous measurements with the Faraday cup. And if we take that charge and if we take these sheath measurements, we do the calculation, we see that even with the flipped sheath, we're not getting the extra force that we need to explain all that extra lofting if the charge has remained the same. So that brings us to the charge measurements. This is a really simple way to do it. We have our dusty surface sitting on an insulator, which is sitting on a metal plate, which is connected to a power supply. Then we charge up our dust with either the UV, the plasma, or the UV and the plasma. We turn everything off. We slide over that grounded mesh grid, and we change the bias on the bottom plate, essentially changing the electric field strength between those two plates, and we try and accelerate those dust particles up towards that mesh grid and catch it with the camera. So this lets us get a relative estimate of charge between all the different methods. And using those previous Faraday cup measurements, we can start putting absolute numbers on things. So these are the maximum charges that we detected across all those different tests on the left-hand side. The first thing of note here is we didn't detect any positive charges, at least in the range of measurement that we had. So this is pretty consistent with the patched charge model, which I described before, so it's all related to secondaries. The other very interesting thing is that when we add our plasma to the UV, we get about a factor of 2 or 3 increase in our charge, which is commensurate with that increase in lofting. So we have some thoughts on why this might be happening. In the original patch charge model, you had secondaries being emitted and then reabsorbed in microcavities in the dusty surface. This leads to close proximity patch charges of like charge patches, which gives you large repulsive forces, which gives you that lofting. We propose an addition where the ambient plasma electrons are absorbed by those positively charged photoemitting patches, neutralizing them, allowing you to pump more charge into that microcavity until a new equilibrium is reached, generating larger forces, which gives you more lofting and which lofts larger dust particles as well. So in the context of the illuminated surface of a rocky low atmosphere body, such as the day side of the moon, we would typically think that the charging is dominated by photo emission, by photons, and that the low density plasma, or at least the low energy component, doesn't have an effect because it's not generating secondaries. So we may actually be significantly underestimating the amount of charge and underestimating the mobility on that side, if that's what we consider. Now, the key points here, we observed that exposing photo-emitting dust particles to a low-density plasma enhanced the charge by about a factor of 2 or 3, which led to an enhancement in the lofting, the mobility, by about the same factor. So we think that's due to ambient low-energy electrons neutralizing those photo-emitting patches, allowing you to essentially pump more charge into those microcavities, and we would call that photoelectric charge pumping. Now, this kind of underwrites why we need to send instruments that would actually measure this charging environment, measure the photoelectron sheath, measure the plasma sheath. For that, you can refer to Tuesday morning's talk, I think, on the double hemispherical probe. Now, what I have here is a spectrum of the solar emission in what we would call the vacuum ultraviolet region, so about 200 nanometers to 100 nanometers. For all intents and purposes, as you go down in wavelength, you would expect to see more photo emission. So for that lamp that we were using for the experiment, we were about 172 nanometers. So we're at the high wavelength, low energy part of that scale. So it's important, I think it's important at least, to see what happens with this charging, what happens with this mobilization for different intensities of light, for different wavelengths of light. And that'll help inform what happens on the moon in different illumination conditions, or perhaps in during solar events. So the majority of my PhD work is spent building radiation sources that mimic this part of the solar spectrum. So I have been doing that sort of work, but that's probably another like 10-minute talk. So I think what I'll do is I'll leave it here and I'll just say thanks for listening.